Consider two square matrices, A and B. Then B is similar to A. If there's an invertible matrix P such that the matrix B is equal to the inverse of P multiplied by A multiplied by P. So this means that B and A have similarity in variance or properties shared by both matrices. So these properties include that A and B are both invertible, they have the same determinant, the same rank, the same nullity, same eigenvalues, and same eigenspace dimension. So in other words, if B is a simpler matrix, for example, a diagonal matrix, then it's easier to calculate these properties for a diagonal matrix, and they'll be the same for our original matrix. A square matrix A, so for example it has R rows and R columns, can be diagonalized or made diagonal if there's an invertible matrix P such that the inverse of P multiplied by A multiplied by P results in a diagonal matrix. So in other words, in this case, P diagonalizes A. So therefore, if a square matrix A with R rows and R columns is diagonalizable, then it has R linearly independent eigenvectors. And these eigenvectors don't necessarily correspond to distinct eigenvalues. So the first step to diagonalizing a matrix is to find R linearly independent eigenvectors. So as we've done previously for our example matrix, we calculated the eigenvalues using the characteristic equation being the determinant of A minus the scalar lambda by I is equal to 0. And then for each eigenvalue, we solve the following equation. So we subtract lambda from the diagonal entries, and that's multiplied by a vector V is equal to 0. And from that, we're able to represent our eigenspace in parametric form, with these eigenvectors being the basis vectors for each eigenspace corresponding to the separate eigenvalues. So what we do is merge the basis vectors in each eigenspace into a set S. So here we have two basis eigenvectors. And then from this set, we form our matrix P by placing each of those basis vectors in the column of the matrix. So we have 2, 1 and minus 1, 1. And now if we invert this matrix, we have the reciprocal of the determinant, so 2 minus negative 1. And then we swap A and D and then negate B and C, as we've done previously. And now if we multiply the inverse of P by the matrix A by the matrix P, then we expect to get a diagonal matrix with the entries on a diagonal being the eigenvalues of A. So that will be 5 and -1. So each of those eigenvalues corresponds to the eigenvector in each column of P. So as we can see, 5 corresponds to 2, 1, and the eigenvalue -1 in the second column of the diagonal corresponds to the eigenvector -1, 1. And I encourage you to actually evaluate this product to verify this result. So again, A, in this case being a 2 by 2 matrix, can be diagonalized if we have 2 linearly independent eigenvectors, which we do in this case, to form our matrix P, also being a 2 by 2 matrix. One application where diagonalizing a square matrix becomes handy, so we had D being similar to A, so in other words it's equal to an invertible matrix P by A by P, with P having the linearly independent eigenvectors in each column. And D ends up as a diagonal matrix having these eigenvalues in each column of the diagonal matrix, where each eigenvalue corresponds to the eigenvector in that column, as we saw. Now if we square both sides, then we have D multiplied by D is equal to the inverse of P by A by P, and that's multiplied by P inverse by A by P. And P by its inverse gives the identity matrix, so we end up with P inverse by A by I multiplied by A, which is A, by P. And now we'll write this as D squared is equal to P inverse by A squared by P. And if we multiply both sides by P, and then by P inverse, then what we get is A squared is equal to P by the square of the diagonal matrix by P inverse, where D squared has the squared eigenvalues of A on a diagonal. So repeating this process, this equation generalizes to A to the power of some exponent is equal to P by the diagonal to the power of some exponent by P inverse. So as you can imagine, computing the powers of A, for example A to the power of 20, means we need to multiply A by A and so on 19 times. But in this case, we'd only have 2 matrix multiplications. So for example, let's calculate A squared. And previously we determined P and P inverse by putting the basis eigenvectors in each eigenspace in the columns of P. And remember, our diagonal matrix had the eigenvalues on a diagonal and zeros otherwise, where each eigenvalue corresponds to the basis eigenvector placed in each column of P. So 5 corresponds to 2, 1, and the eigenvalue -1 corresponds to the basis eigenvector with components -1 and 1. So to obtain a to the power of 2, we multiply p by the diagonal matrix raised to the exponent, being 2 in this case. So d multiplied by d is the same as squaring its entries on a diagonal. And we multiply this by p inverse. And if you evaluate this product, you'll get the same result as multiplying a with itself. So I'll leave that for you to verify as an exercise. The geometric multiplicity of an eigenvalue lambda is the dimension of the eigenspace corresponding to lambda. So for example, our eigenvalue lambda 1 is equal to 5 has an eigenspace with a dimension of 1. So therefore the geometric multiplicity of lambda 1 is equal to 1. And similarly, the eigenspace corresponding to lambda 2 also has a dimension of 1. So the geometric multiplicity of lambda 2 is also 1. Now the algebraic multiplicity of an eigenvalue is the number of times it appears as a factor in the characteristic polynomial. So for example, remember that we obtained the characteristic polynomial of a by taking the determinant of a minus lambda I and setting that equal to 0. So what we have is the determinant of a minus lambda I. So we subtract lambda from the diagonal entries, and we obtain 3 minus lambda by 1 minus lambda minus 4 by 2 is 8. So therefore we have lambda squared minus 3 lambda minus lambda is minus 4 lambda plus 3 minus 8 is minus 5. And this is our characteristic polynomial, which we factorize as lambda minus 5 by lambda plus 1. So in this case, lambda 1 appears once as a factor in the characteristic polynomial. So the algebraic multiplicity of lambda 1 is also equal to 1. And lambda 2 also appears once as a factor in the characteristic polynomial. So the algebraic multiplicity of lambda 2 is also 1. Now the geometric multiplicity of an eigenvalue is less than or equal to the algebraic multiplicity for every eigenvalue of a. And also a is diagonalizable if and only if the geometric multiplicity of an eigenvalue is equal to the algebraic multiplicity for every eigenvalue of a.